Okay, so now we're talking about chemical equations, okay? So these are the notes. We've already gone through a bit of it, but just as a quick review here, we know that there is what is called a skeleton equation, and that's when an equation is not balanced. We're going to talk about it in just a second. And then there's a balanced equation. Okay, do you remember? RAP, it goes reactants, arrow, then what? What is P for? Products, very good. So reactants, arrow, products. And sometimes you can even use A. Some people will use A and put the atoms in there in the middle to see like what atoms are on both sides. Remember, the big idea is that by the law of conservation of matter, what you have on your reactant side, you still have on your product side. It's just a matter of rearranging the atoms, okay? That's all that happens in a chemical reaction. So what we're gonna do today is we're gonna do talk about 5 different reactions, and some of them I'm gonna demo for you, okay? So we were talking about making s'mores, and you can actually set up ratios. This is really good for standardized testing. How can you set up a ratio? Well, what I can do is, I can say, for example, if I wanted a ratio between the Hershey's rectangles and the graham crackers. So the pieces of chocolate versus the graham crackers. And I'm just gonna write crackers instead. So let's just write crackers here. Well, what I can do is come up with a ratio, and my ratio is how many pieces of chocolate? 6 to how many crackers? 4, okay? And it's a baseline ratio. Now there are 2 other ways that I can write this ratio. You can also do it as a fraction, okay? So what I can do is I can say 6 pieces of chocolate to 4 graham crackers, okay? Or I can flip it, and it's still a ratio. I can say 4 graham crackers to 6 pieces of chocolate. These are all called ratios, okay? And ratios can be used in a calculation really, really easily. For example, let's say that I told you that you had 20 graham crackers and you wanted to know how many pieces of chocolate you needed in order to make as many s'mores as you could with the 20 graham crackers. You want to use up all your graham crackers. Bless you, okay? So I want to use up all the graham crackers that I have. So what I'm going to do is I'm going to throw in one of these ratios into a multiplication here. And when I do this, just like when we say, what's 1,000 divided by 1,000? 1. I'm seeing 1. What is x divided by x? 1. What is graham crackers divided by graham crackers? Do you see the pattern? 1. It's always 1. So if I put graham crackers down here on the bottom, algebraically, my crackers will actually cancel out. But to set up a ratio, what I'm looking at then is I'm looking at the one that has crackers, which is 4 graham crackers to 6 pieces of chocolate. And now what I can do is I can figure out 20 times 6, which is 120, divided by 4 is 30. That tells me how many pieces of chocolate I would actually need in order to use up all of my 20 graham crackers. I would need 30 of those little, the little brick pieces, like the little tiny pieces. So that's how ratios work. Again, really good if you're doing a standardized test next week and they're asking you like story problem questions where you can set up a ratio, and ratios are super, super, super helpful when it comes to math, okay? So here it says, let's balance a water equation. Now, I think I explained to you, we're not gonna be balancing equations. It usually takes about a week to do it, but it's really good to know. Again, these come up in standardized tests too, chemical equations do. And so having a good idea of like, what are the numbers representing in front? Do you remember, it's a word that starts with a C, it's really long. What do we call the numbers that are in front of a balanced equation? You can just say it. Coefficients, awesome, they're called coefficients. And the coefficients give us the ratios, okay? So what we're gonna do is, we're gonna try to figure out what the coefficients are in this equation to make water, okay? So what we do is, I've got my atoms, and on both sides, you can see that you only have hydrogen and oxygen, okay? So on both sides, I am simply seeing those 2 elements. On the left, how many hydrogens do I have? Well, if there's a little 2 there, that means I have 2. And on the right, how many hydrogens do I have? I also have 2. Very good. Now for the oxygen on the left, how many oxygens do I have on the left? 2. Very good. And how many oxygens do I have on the right? There's no number, which means 1. Very good. I'm going to switch colors here. And now what I want to do is I want to try to get it so that they're balanced. Okay. So right now, I got 2 and 2 for my hydrogen. So that's good. But my oxygens are 2 and 1. So I know I need more oxygen. So people will say, don't do this. They'll say, so write a 2 in there. Okay. Here's the situation. Here's the issue. H2O is water. H2O2, I don't know if anybody, you can guess at what you think it might be. H2O2 is something that you can gargle with. It does show up in toothpaste. You cannot drink it. You shouldn't be swallowing it. You can put it on your cuts because it'll actually sterilize too. So it'll get rid of anything like that. Anybody want to guess? Hydrogen peroxide. Yes, it is. It is hydrogen peroxide. So that's hydrogen peroxide. So you can't just change it and throw a 2 in there because what you're doing is you're changing the formula and we don't want to change the formula for it. So instead what we want to do is we want to only change the coefficients. So only the number in front can change. So that I can make a 2. That's fine. I can put a 2 there. And now it's 2 waters. Okay. Well, what does 2 waters look like? Well, water is H2O. And if I have 2 waters, then it looks, and you would never have to do this, by the way, okay? So what I would do is then you're actually multiplying. So how many total H's do I have if I have 2 waters? 4. And how many total O's do I have? 2. So just looking at this, you actually have to use the 2 applies to the entire thing, okay? So now that I have 2 H2s, how many total H's did we say we have now? 4. So I'm going to cross that off and I'm going to make it a 4. How many O's do I have? I had 1, but now I have 2. So cross that off. Now on the other side, okay, this is fine. My O's are fine. Those both have 2. But look at, now my H's are off. So there are 2 H's here. I want it to be 4. What can I do to the H's to make it 4? Put a 2 in front. Awesome. Put a 2 in front there. And now it's a balanced equation. Because now I have 4 on this side and I already had 2. And now since my atoms are equal on both sides, it's no longer a skeleton equation. We call it balanced. Okay. All right. So now let's take a look at chemical reactions. So let me give you a little bit of maybe extra information here. Okay. So in the 1960s and 1970s, they made a big change in education. Okay. One of the situations that were happening is people were doing what is called, what I kind of call garage or basement chemistry. People were dying. People were burning things off their hands. They were losing fingers. And so what they said was, from then on, they said, let's make this so that every student, every high school student takes chemistry and learns about chemical reactions. Okay. That was something that was really important at the time because they had so many accidents. And so since then, things did decrease. Why? Because when you're more knowledgeable, you're less likely to make a stupid mistake, right? You have more knowledge and you have a better understanding. So they said, we're not going to totally teach them everything about it. You don't have to be at like a college level of chemistry, but at least to kind of give you an idea of like, what happens when you mix 2 chemicals together? What's actually going on, okay? So that's what we're doing here. Now, even if you take a college level class, so let's say you decide you want to go into pharmacy, you want to go into medicine, you want to be a nurse, you want to go into engineering. Even engineers actually will need to take chemistry in college at the university level. There are still only 5 major types of reactions that are very basic. Combustion, single displacement, double displacement, synthesis, which is also called combination. That's the one that is combination, is synthesis, and decomposition. Those are the 5 major types, okay? So we're gonna start with combustion. The first thing I'm gonna do is I'm going to show you a combustion reaction, and it's right here. This right here is what I'm gonna show you. This is called methane. Okay, it's called methane. And what I might get a chance to do in the future is I might get a chance to actually let somebody set my hand on fire with the methane gas. So I'm gonna come over here, and what I have here is, let's see if I can kind of get a good angle here. What I have here is I have my gas valve, okay? And if you guys know this, I'm not sure how well you know this, but in your homes, you have methane gas that comes out. You can actually access methane gas from your homes. The gas lines that go around your homes and it says like, do not dig here, that's because they're filled with methane, okay? So what I'm gonna do is I'm gonna turn this on. And when I turn this on, I let the gas go. And what eventually will happen is if I light this, then I can get a fire here going. And this is burning of methane. Anybody want to tell me what you think would happen if I just let this go through the room and then lit the match? The room, it would explode. We would have a huge explosion. So if I just lit one match with the methane gas all around, then we would have a huge explosion in the room, okay? So very dangerous. That's why they add a smell to it. It doesn't normally have a smell. It smells like sulfur. That way you know if there's like a gas leak, for example, okay? So what I'm gonna do is I'm gonna control it. We don't usually do that. So I'm gonna control it. What I have here is, I have what is called a Bunsen burner. So I've got a, like a rubber, I don't know if you guys can see this in the back. So I've got this here, it kind of lines up. This is nice because I can adjust it. I can adjust how much oxygen I give it. I can adjust the amount of gas. So there's a man by the name of Bunsen that came up with this. Okay, so I'm gonna do the same thing, but now it's gonna be a controlled flame here. So let's light this. Okay, and definitely more controlled than that one, right? Okay, so watch what I can do here. If I close off the oxygen, good. Turn it down just a little bit here. Okay, so if I close off the oxygen, we know oxygen does what to a flame? It feeds it. Oxygen feeds a flame. So if I close this off, let me see if I can show them in the video first too. So I'm going to close off the oxygen. Look what happens. It's orange. It turns orange. And I can do this. I would not do that to a blue flame. The blue flame is really hot. The orange flame, I can do this too. The blue flame, I would definitely not do that too. It's a lot hotter. Okay, question? Yes, yes. Okay, because a lot of times it depends on the percentage too. So if you just do straight alcohol, you can burn your hand pretty badly by doing something like that. Okay, so this is hot here. What I'm going to do is I have some magnesium, and magnesium is, so let me just kind of come around and show you guys here. It's a piece of solid and it's bendable. So, so you can bend it, it's malleable, I can hammer it into shapes, it's ductile, but you can see it's kind of like silvery in color, and I'm definitely like bending it all around and stuff like that. What I'm gonna do is I'm going to combust it, okay? When I heat this, it doesn't actually melt, it will burn, okay? And when things burn, they burn in oxygen. Now, I don't want you to look directly at it, so once the light, it's gonna be a really bright light, I want you to look over my shoulder, okay? So I want you to look this way or this way. You're going to see, I'm going to be looking at you. I won't be looking directly at it. Okay. So you'll still be able to see it because I don't want you to hurt your eyes. Okay, here we go. So yesterday when I did this, the smoke alarm, the fire alarm went off like just as I was doing it. I was like, I promise you that was not me. So that was a test. It was just, they were just running a test. Okay, so let's put this in. Let me make sure they can see this. I think you can. Yes, you can. Okay, watch how bright this is. You see how bright that is? It's like a super bright white light. They use this to set off other reactions that need a high amount of heat. Oh no, I dropped it. Okay, so I'm gonna show you guys this. I didn't want to drop it because I wanted to show you first. All right, so look at this now. Okay, I don't know if I can pick it back up again. Okay, now it's actually a white powder. It's gonna fall apart in just a second, but I wanted you to see it first. So now it's no longer that solid piece. Oh no. So now it's like it's all powder. So it's like this white powder that is, it's no longer magnesium anymore. Now when magnesium got added to it, it's actually called magnesium oxide. Okay, so kind of want to show in the video here. So now it's like, I don't know if you can see this, but it's like this white powder now. It's no longer those metal pieces, okay? So that's the magnesium oxide. All right, let's come back over here. All right, so let's write this reaction down. So this reaction is, it's magnesium, which is Mg. Oh, let me switch my color back here. It's Mg plus O2 is oxygen. And what we actually did is we got MgO. Now, usually when you combust something, you get carbon dioxide and water, almost always, but it doesn't have to be. This is combustion because of the oxygen on the reactant side. As long as you have oxygen reacting on the reactant side, it's combustion. But this is also synthesis or combination because I'm taking two things and combining them into one. I'm combining into one substance. So again, even though it's combustion, so if you were asked, and it was like a question, it was a quiz question or something, you could put synthesis or combustion for something like this. You'll get the answer right, okay? All right, the next one, single displacement. So what I have for single displacement is I have some copper chloride here, and it's kind of this cool, like bluish colored stuff. So it's copper chloride. So there's copper in this, even though it doesn't look like it has copper in it. And what I'm going to do is I'm going to take a piece of like literally just like a piece of aluminum foil. And I'm just going to break a small piece of aluminum foil and I'm going to drop it into my test tube here. Okay, and now I'm going to, so just a piece of aluminum foil, I'm going to add some of this kind of like bluish colored copper chloride to it. And let's check to see what happens. And I already have one that I did this to, so you can already see what ended up happening. We just did this last hour. Okay, so what's happening is my aluminum foil is disappearing. It's bubbling a little bit, but it's turning into this reddish brown stuff. The reddish brown stuff, so I'm going to show you guys what it looks like here. So it's changing now. This is the one from last hour. It's changing, and the aluminum is going into the solution, and the solution color is going to change from blue to clear. The aluminum's going away, and guess what's coming out? Guess what this reddish stuff is? It's copper. The reddish stuff is actually copper. So it's copper in like the powdered form. So this, what happens in single displacement is they switch places. So what happened is the copper switched places with the aluminum. So the aluminum foil is going away. It's not really going away. It's just going in a solution. So what happened here is I had aluminum foil and I added copper chloride. It's actually CuCl2. And when I did that, the copper swapped places with the aluminum. So the copper comes out as copper solid and the aluminum goes in, and it's actually AlCl3. The aluminum goes in, and now you don't see the aluminum anymore because it's an ion. It's an ion form, okay? And if I balance this equation, I'm going to balance both of these actually. I would need a 2 and a 2, and on this one, I would need a 3 here, and a 2 here, and a 2 there, and a 3 there. Okay, and again, you don't have to worry about balancing it, okay? So I call this like player substitution. Who plays a team sport and tell me what team sport it is? Football, football, any other team sport? Volleyball, punching, okay. Soccer, okay. Now, in team sports, what happens is you have one person that is sitting on, that's bench, it's sitting on the sideline, okay? Let's say that your goalie in soccer goes out. Who are you going to replace your goalie with? Another goalie, right? You don't want to replace him with your forward. You're going to replace him with your goalie. So it has to be the same type of player. If we look at the periodic table, aluminum and copper are both metals, so they can switch places, okay? All right, double dating we already did. So in this one, what we did was, and I'm going to show you in a second, we took potassium iodide. This was the flint one that I was talking about. And we had lead nitrate, which is PbNO3 too. And what happened was the potassium switched places with the lead. And so it's like double dating. You've got two compounds and then they're going to switch places. And so that's called double displacement. And when we did this, these were both clear. So that was clear and this was clear. And when we did this, we actually got this yellow solid to form. So this yellow solid is actually PB is now with the I, PBI2. And this is a yellow solid. And what's left behind is called KNO3. KNO3 is safe in small amounts. In liquid, it doesn't really do anything. But if you isolate it and you get a lot of it, it's fertilizer. It can be used to make bombs. Okay. So KNO3 is safe in like small amounts, but that's the yellow stuff. And so what I can do is I can isolate. They call those precipitates, so I can isolate that. Okay, synthesis is pretty easy. We already did it. Let's just rewrite it. Magnesium plus the oxygen gave us MgO. So we're going to just use the same one there. So again, we're taking two things and combining them to make one. And the last one that we're going to do, I'm not going to show you this, I can show you another time, is decomposing water. What you can do to water is you can use what is called electrolysis. You're basically like electrocuting the water. And what you do is you'll see bubbles. When you take two wires and you plug them, you drop them into the water, you'll see bubbles. Those bubbles are actually hydrogen and oxygen gas. So you can actually decompose the water. And if we balance this, we would actually get a 2 here and a 2 there. And so you can take water and turn it into gaseous hydrogen and oxygen. Okay. So those are the 5 reactions. So hopefully now a decomposition is you start with one thing and it breaks up. Synthesis is you start with 2 and you make 1. Double dating is 2 swap versus single displacement is one is on the bench and then they switch. And then combustion is burning with oxygen. Okay. So those are the 5 major types of reactions. Hopefully that helped, and happy day to you.